Okay, so now I have all of my information sort of written down. Some of this is going to be useful, some of it won't. Again, as a person solving this problem, I just want to write down every possible useful piece of information. So let's begin with part A. We are told there are two stages to consider, namely the collision and then skidding to the halt after the collision. Now, when I look here, the information they've given me is something that happens after the collision. So here's what I'm going to do. I'm going to work backwards. And my idea here, my strategy is let's examine after the collision and then work to get the initial van speed. Okay, so here's going to be my idea. I'm going to work backwards. So let's look at after the collision. And I'm going to tell you right now, I had two formulas that I looked at. This one and this one. Well, they're giving me masses here. So it may be the case that I can use v squared equals u squared plus 2as, but they've given me so much information about forces and masses, I'm really tempted to use the work kinetic energy formula. So that's my judgment call, and that's why I'm going with work equals delta Ke. So to this end, what's the force that's actually doing the work to stop both cars? It's the friction force on the car times the distance that we go through. And I'm going to write a negative sign here to indicate that the car is moving forward, but the friction force acts backwards. And the effect is that I come to a final speed of 0 from an initial unknown speed. Now the force is actually acting, it's doing work on both the car and the van to slow them both down. So let's put in our numbers. This is going to be negative 2400 times that distance of 15 equals 0 minus, now I'm going to add these two masses up, that's mass of the car plus mass of the van, that's 1/2, times 1000 times the initial speed squared. This is their together speed, their speed traveling together. And when I go ahead and actually isolate u, that speed is going to end up being, well, before I actually do that, I realized the sum of their masses is 1200 plus 800, which is 2000 kilograms. So I need to correct that. Let me go ahead and get that speed. And when I do that, that's going to be 24 over 20 times 15 under square root. So that's 4. So it's, let's see, that's 3 divided by 4, 3/4. So sorry, that's going to be 24 over 10 times 15, which ends up being 36. So u ends up being 6 meters per second. This is the speed of both after they collide. Okay. So, if we continue on this idea here, again, and let me just double check one thing. Yeah, so that speed's right. All right, now for part B. This is both of them after the collision. Let's actually talk a little bit about what's going on here. So what we're saying, if I were to draw a little picture here, is we've got the van, we've got the car, and what we just examined is after the hit. That's a really bad, so hit H-I-T, they hit here. What we just looked at is Here's the van, here's the car together, and then they stop, and we just found the speed here. What we're saying, though, is we want the speed of the van before the collision. Now we're going to use conservation of momentum. So mass car, V car, plus mass van, V van. Sorry, we need initials. Mass car, U car, plus mass van, U van, equals mass car, V car, plus mass van, V van. Let's put in our numbers. So the van is moving. The car is not. So this is 0 times 800 plus 1200 times the speed of the van, the velocity of the van that we're solving for. And what happens is we have the car moving at 6 and the van moving at 6. So we have 800 equals 2,000 times, we have 1,200 U of the van equals 2,000 times 6, which is 12,000. And so when we get U of the van, we actually end up getting 10 meters per second for the speed of the van. That's part A. Let's go ahead and take a look at part B. Okay. So the driver sitting in the car was wearing a safety belt and had a headrest. We want to know whether the headrest could serve a protective function in this particular accident. Let's be really clear here. Okay. Let's talk about student intuition. Here's what happens with student intuition. What student intuition does is they look at this and they say, this is the vaguest question ever written, and I hate it, and I'm just going to write things down and pray. And unfortunately, the IB knows that you're going to do that, so I would try to write something, but I'll tell you right now, I'll be able to tell after 3, it's going to be very hard to get partial credit on questions like these if you write nonsense. And that's a little bit harsh to say. I feel your pain because I used to do the same thing. That's the only reason I'm calling it nonsense. Because deep down inside, I look at my own work and realize, I'm just winging it here. Let's be clear on what's going on. We need to look at the physics before the collision. We need to look at the physics at the collision. And then after the collision. Okay, that's what they want us to look at. So let's look at what a safety belt does. So here, we'll write this in blue. So during the actual hit, okay, the person in the car is at rest and wants to remain at rest. So the safety belt doesn't really do anything at first to keep the person at rest. And you know what I would throw in here? I would throw in that this is Newton's first law. Okay. Now, after the collision, the person now is moving and wants to stay moving. As the car skids to rest, the person is sliding forward, and the seat belt keeps them in their seat. Once again, let's also refer to this as Newton's first law. Okay? Because that is the rule. So that's it for that. Now I get to cheat a little bit and paste this here and adapt this explanation now for the headrest. So, let's be clear. During the actual hit, the person in the car is at rest wants to remain at rest. The headrest pushes their neck forward with the rest of their body and prevents whiplash. After the collision, the person not moving wants to stay moving, so the headrest and its effect of pushing the person's neck doesn't really do anything to protect them. So that's the answer. See, notice I refer to a very specific law of physics. These are the kind of answers they want. So you always have to ask yourself, what's the law of physics? Do not use words like words to avoid. Do not use words like cushion or soften, or you need extremely specific physics words, or the mark scheme is not going to give you any points. All right. So this is it for the very first problem on the problem set for practice.